Welcome to the second day of our Computer Science 2019 Capstones. With us now is Alex Heiting.
Yep.
He's going to tell us about Shall We Listen?
Shall we listen? So, hello, as Perry mentioned, my name is Alex Heiting. I am a senior here at Carthage College, and today I am going to be presenting on my software-defined radio senior thesis project entitled Shall We Listen? So, what problem am I solving with my project? So, about 2 summers ago, I was starting to become more and more involved with 2 of my biggest hobbies, which are aviation and cars. And for myself, I wanted to become more involved with those 2 specific hobbies, and that includes listening to different types of frequencies that both environments include. So for the race cars, I wanted to listen to different frequencies at the racetrack for the car to the pit crew to talk about strategies or possible problems that they're coming across, just as another way to involve my, likeness with the hobby. And then also with aviation, I wanted to listen to the contact from the air traffic controllers to the planes and vice versa. Again, just to try to get a little more immersed with my hobby. So this is all fine and dandy for the racetrack because I could buy one of these radios for $25. And this allows me to receive stuff like FM radio, but also stuff at a racetrack. Also other things like the NOAA weather radio, because why not? They're small, they're cheap, only $25. Except I ran into the problem that aviation radios cost, for the same size, $150 to $200. And as a broke college student, I can't really afford that for something I'm going to use maybe 2 or 3 times out of the entire year. So I came across a possible solution to my problem through software-defined radio. In other words, radio that is built through software on a personal computer. And I first came across some solutions with some pre-built software, but I found that those to be a little clunky and a little settings eccentric. Or in other words, there's too many things that you have to learn and to understand about those programs in order to use them properly. So I made it my personal goal to go out, receive a wide variety of different frequencies, the ones that I particularly wanted to receive, which included aviation and race car, but also to make something that was super, super simple and easy to understand for a user, someone, for example, like Jordan, who maybe has never tried anything like this before, doesn't want to mess with any of these settings, and just click a button and start listening. So I wanted to make it so that it was very, very simple and easy to understand. So what am I going to talk about today? First, I'm going to talk about the science behind the radio. I'm going to talk about my software development. I'm going to demonstrate my project for you guys, and then I'm going to talk a little bit about some extra stuff that I learned along the way. So before I could develop my software, I had to understand how the science of radios work. And in doing so, it allowed me to develop my actual software more effectively than if I would have just started diving right into it. So all radios today use what are called continuous sine waves to transmit information, whether that be audio, video, or data. It doesn't really matter, anything like that. Each different radio signal uses a different sine wave frequency, and that is how they are separated. So any radio setup has 2 parts, a transmitter and a receiver. Transmitter, it's pretty straightforward, takes some sort of message, whether that be the sound of someone's voice, pictures, anything like that, and it encodes it onto a sine wave and transmits it via radio waves. The receiver then receives those radio waves and decodes the message from the sine waves that it receives. And just as a fun little bit of trivia, this right here is a picture of a Marconi transmitter receiver, and this is from the early 1900s. This is one of the first radios ever built. A little fun fact about it is back when the Titanic incident occurred, there were multiple different broadcasts using this similar type of radio on those ships that were in the area near the disaster that were transmitting information to the mainland America. And it was actually mostly false information. So then a bunch of news stories were run on false information, and it wasn't a couple weeks until the general public actually knew what happened during the incident. So because of this, the U.S. government created what we now know as the FCC, or the Federal Communications Commissions, from this disaster. So now I'm going to talk about the science behind the actual analog radio. And analog radio first started in the 1900s with AM radio, and then in the 1930s with FM radio. So first off, we have the carrier wave. A carrier wave is a waveform, usually a sine wave, that is modulated with an input signal for the purposes of conveying information. So it's not just a sine wave that you need, though, to convey that information. As I mentioned, you have to modulate that wave, as a sine wave itself doesn't carry any real information with it for the purposes of what radio transmissions are. In order to encode some information with it, you have to modulate the sine wave. And the three most popular modulations are pulse modulation, amplitude modulation, and FM modulation. So in pulse modulation, you simply turn the sine wave on and off. It's not that common, but as you can see, one of the possible uses for it would be Morse code, because Morse code is a small transmission, silence, transmission, silence, transmission, and so on and so forth. So with this modulation and this sine wave, the modulated result creates this, a wave that actually is compressed when it's actually transmitting information, and when it's not compressed, then it's not transmitting any information. So as I mentioned, this is most useful for Morse code, but another thing that it is used for is also radio-controlled clocks. So any form of like the clock in the back of the room, for example, anything like that throughout the entire United States is actually being controlled via one pulse modulation transmitter. So pulse modulation is very popular in the sense of broad range. It isn't very useful because all it does is tells you on or off or sends one little bit of information, but it is useful for how broad of a range that it does have. So then we have amplitude modulation. And amplitude modulation, the actual amplitude of the sine wave changes. In other words, the peak-to-peak voltage of the wave. So peak-to-peak here. So this is a standard modulation, and this is the standard sine wave. And when you put the two together, this is what you get. A wave where its actual peak-to-peak voltage changes based off of the information that is being transmitted. And then last up is frequency modulation. And in frequency modulation, the transmitter's sine wave frequency changes very slightly based on the information signal. So again, here we have the modulation wave, which looks very similar to the amplitude modulation, except this one's different because the peak-to-peak does not change. Then we have the standard sine wave, and when you modulate them together, you could say it's a mix of pulse modulation with a little bit more to it. So you have the waves themselves that are actually combined or compressed for certain forms of information, but then you can see they're spread out and they're compressed again, but they're not as compressed. So it all depends on the actual information that's being transmitted on these waves will determine the actual shape of the wave itself. So why do people use frequency modulation compared to all these other two that I just talked about, or all of the three that I talked about? It's because frequency modulation is the one that's mostly immune to static. So if you listen to AM radio in your car or something, if you ever do that anymore, you'll notice that sometimes it's pretty staticky, but FM radio doesn't seem to be overly staticky, at least compared to AM radio. Another reason why FM is very popular is that, well, it's useful for tons of different things. So for example, the little clickers in your remotes for your cars, to like lock and unlock your cars, that's also a form of frequency modulation. So the frequency of a sine wave is the number of times that it oscillates up and down per second. FM radio signals are operating in the range of around 100 million hertz. So for my demo later on, 91.1 FM is right around 91,100,000 cycles per second, otherwise known as hertz. So now I'm going to talk a little bit about the hardware behind analog radio, and I'll explain why in a little bit. So first off, how does the radio receive the transmission and extract the info? The first thing you need is an antenna. So you could have an antenna like the one here on the PowerPoint, or you could have an antenna on this little tiny radio, or an antenna that I have over here for my actual project. Doesn't really matter, but an antenna, what it does is it actually picks up all the frequencies out of the air. Doesn't matter if it's a frequency that it actually wants to receive or not. If there's a frequency in the air, the antenna will pick it up, because it's the job of the tuner that will actually tune out those other frequencies that you don't want to receive. So the tuner picks out the frequencies you want to listen to, and the tuners work using a principle called resonance. That is, the tuners themselves resonate at and amplify one particular frequency and ignore all the other frequencies in the air. Then you have the demodulator, and the demodulator is the actual module that extracts the information out of the sine wave. So once it gets picked up through the antenna into the tuner, gets the actual frequency you want to listen to, then it goes through the demodulator. It demodulates based off the type of frequency it is. So if it's FM, it goes through a frequency modulation, demodulator. AM, an amplitude modulation, demodulator. And then you have the amplifier, and the amplifier will actually convert that demodulated signal into a form of a sound and amplify it into something that you can hear through your speakers, whether that be speakers, headphones, earbuds, anything you want to listen through it. That's how it does it. So now the science behind SDR, or software-defined radio. So software-defined radio is a radio communication system where the components that have been traditionally implemented in hardware, so amplifiers, modulators, demodulators, that sort of stuff, are instead implemented by means of software on a personal computer or an embedded system like a Raspberry Pi. So while the concept of SDR is not new, the rapidly evolving capabilities of digital electronics render practically many processes which were once only theoretically possible now possible. And the reason why I learned so much about the analog radio, you might have picked up on what I just said, is I developed my software-defined radio through the process of mimicking the hardware aspects of a traditional radio. So I had to understand how a traditional radio worked in order to develop my software version of the radio. So a basic software-defined radio system may consist of a personal computer, so my personal laptop here, a desktop, anything like that, with a sound card. For my purposes, it does need a sound card. Some form of analog to digital converter, which is what this little guy is, and I'll touch on this in just a minute, preceded by a form of an RF front end. And significant amounts of signal processing are handed over to your general purpose processor on your computer instead of having special purpose hardware built to do that instead. So the actual hardware, so I am using the RTL 2832 USB adapter, and it only cost me $25. These little adapters were originally designed to use or to receive DVB TV channels. So in other words, digital video broadcasting TV channels. And with a simple driver change that some people developed and discovered in the early 2000s, they realized that you could change the drivers in this and you could pick up almost any frequency you want within reason. So these little devices are good for right around 24 megahertz all the way up to 1500 megahertz. And then you can go up a little bit further, but sometimes that reception does get a little finicky. So then there are multiple different versions of this type of device. I chose this specific device because it's pretty cheap. You can find them as cheap as $10 all the way up to $400, and it just depends on what you're trying to do. The more expensive they are, the more accurate they're going to be. So if you're doing it for research purposes, you're going to want to spend a little bit more money, but you can get away with a cheap little $25 adapter for the purposes of what I am trying to do here. So my software development. So I developed my program in blocks of code through the GNU radio library. So I'm going to go through now and demonstrate what it took for me to make an FM receiver through software. So the first thing that I had to do was figure out the source for my reception of my radio. In my case, it was my RTL little driver. So using the tools to block it with the blocks of code, I basically needed to get the settings right, and that took a lot of time, a lot of research, and that's why I had to do all that research beforehand to really understand how all of this worked, and a little bit of guesswork as well, because you can't go wrong with a little bit of guesswork along with some educated guesses. But some of the settings I had to deal with were the sample rate, which is the actual number of samples per second from the device sending information to my actual computer. Then I had to deal with the frequency, which not that hard. You just dial in the frequency you want to listen to. Then I had to find the settings for the overall sensitivity of the device. And this one was very tricky to dial in correctly, because I noticed if I was building my aviation radio, for example, the settings were completely different in my sensitivity of my device compared to an FM radio receiver. So for the FM you're going to hear later, my sensitivity was right around a numerical value of 20 within the settings of my software. But for my aviation radio, it's actually right around 4950. So it's just a much more sensitive frequency that you have to tune into. So I had to deal with a lot of different sensitivity issues between all of my different frequencies. But after that, then you have the bandwidth, which actually sets the bandpass filter on the radio front end. After that, then we have, back to FM radio anyways, after that we have the low pass filter, which filters out any of the unnecessary frequencies that we're not trying to receive. So even though the tuner itself tunes out all of the frequencies you don't want to receive, sometimes you'll get some audio bleed through, and this low pass filter really filters out all the stuff you don't want to hear. Then you have the wideband frequency modulation receiving block, and that's the actual block that decodes the FM signal into something that's more usable like a sound. Then you have a rational resampler, which converts from one sample rate to another for the purposes of getting a better audio signal. And then you have the actual audio sync, which sends the audio to your audio source on your device, whether it be speakers or headphones or something. So here is a little diagram of all the blocks connected together. Once you have all these blocks formed, then you just need to connect them, which is not overly complex. And then after that, you have a working FM radio receiver on your computer. Now, as I mentioned before, all of the different frequencies that I went to go and receive, all of them were actually slightly different. So for example, my wideband frequency demodulator block would be different on my aviation radio because that uses a form of amplitude modulation. So I'd have to use an AM demodulator. But with that, I actually didn't have to use a low-pass filter. I had to use a high-pass filter because of the narrow bands of the nature of aviation frequencies. So every type of frequency that I went to go and receive, I was not able to use the same blocks of code over and over again. I had to use different blocks of code in order to get something that actually worked right. So now I'm going to go ahead and demo my project for you guys. So this here is my simple little user interface, and all you have to do is click on any one of these buttons and it launches the respective type of frequency to listen to. So I'm going to click on FM radio. I hope this isn't too loud.
The American woman was released to U.S. authorities in Africa.
So here we have 91.1 FM, which is NPR Radio. Jordan and I know that radio station very well. So this is a local Kenosha frequency. In this environment, I can't really demonstrate too many frequencies because of the location of the campus right on the lake, but I can pick up 91.1 FM, and I can also demonstrate 95.1. So if you ever want to change a frequency, all you do is click on the text box, and then you just punch in the frequency you want, you press enter, you give it a couple seconds, and 95.1 is a rock station. But yeah, you guys can hear. So yeah, and then if you ever want to change frequencies, you close out of these little tiny blocks here, and then all you have to do is give it a couple seconds, and it will, my software is set up so that if it does not detect the actual device, it will close out of the program, and that is something that I will talk about in a minute here. Oh. Here we go. So if you want to listen to weather radio, so this is the NOAA weather radio, you just click on that guy, and
See, there are chances for thunderstorms Thursday and Thursday night.
So again, nothing exciting. This is just the NOAA weather radio. This is a radio station located in Racine. There are multiple different stations like this throughout the entire United States, multiple stations for every state, and it's just weather radio. That's all this really is. So now I would love to demonstrate the aviation radio for you, but I can't right now because of where my physical location is. I cannot reach the Kenosha airport from here, but I did take a video of myself when I was out there to demonstrate the capabilities of the aviation aspect. So let me, come on. So currently I'm at the Kenosha Regional Airport. Right over here is the fence for the airport at this old building, and I have my laptop here with my little adapter and my antenna sitting down over here. And I'm going to launch the aviation radio. It takes a minute to load up here. So currently we're listening to the ATIS of the Kenosha Airport.
Landing and parting left at 7 right. Runway 7 left happy is out of service.
So the ATIS radio at an airport is essentially the weather radio that I just demonstrated, except for the airport itself. So it's for pilots landing or departing that airport, and they have up-to-date information about the weather directly at that landing strip. And that's something that's being broadcast at all points in time, so that's why I decided to demonstrate that frequency. But so some of my challenges that I had to overcome, first one was setting up the environment. So as you noticed, I was actually running this through a virtual machine. Before this project, I'd done a little bit of work with virtual machines, both through Perry's classes in the past, but just some tinkering of my own. But I'd never done anything like this before, using USB devices through virtual machines, or really any actual development processes on a virtual machine before. And I discovered some limitations of using USB devices on virtual machines. So if you noticed, like I said, when my program decided to quit there on me, that was because it did not detect my device anymore. So that's something that I've been working with and struggling with for this entire semester. But a simple workaround is you just unplug the device, plug it back in, it gets re-registered through the VM, and then you're good to go. So that's something that I would like to change for the future, but that's something that I had to work with for this entire past 2 semesters. Another thing is receiving multiple different frequency types. In a dream world, I would have loved to have just a simple text box, and you could put in any frequency you want, and you just press enter, and you can just do that over and over again. But I realized, because the nature of the frequencies and my type of device, and like I was mentioning before, the sensitivity of the device between FM and aviation radio, that actually changes. I cannot use one type of batch setting for the device and just run the program over and over again with those blank settings. I have to actually change those settings every single time I want to use the device or use the program. So that's why I had 4 different buttons there to launch 4 different mini programs with all of those settings already set up. And another thing that I had to overcome was the user interface. And while my user interface wasn't anything extravagant, it was very bare bones. That was the whole point of my project, was try to make this as simple as possible. But I'd also never done anything with a user interface before. So it was a fun little challenge to work with making a user interface, and that's something that I know I want to continue doing for in the future. And so some things that I personally would have changed about this, I would change my project by not using a virtual machine, because of those limitations that I discovered with USB devices. Some other things I'd change is, my time management skills. I will admit, I did slack off a little bit there for a bit, and I know Perry had told us at the beginning of last semester, pick a project that you absolutely love, because by the time you're done with it, you're going to just like it. Or maybe not quite hate it, but you're going to be close to it. And I have to say, I don't hate my project, so I didn't quite reach that. And when I first started this project, I thought I loved it. I didn't. I really, really liked it. I did lose a little bit of motivation for a little short period of time there, but that's something that I know I can work on for the future to make myself better, is my own time management skills. But some things that I appreciated is I appreciated my understanding and growth of how frequencies work for radios. I also appreciate my growth through working with Python. So my entire program was written in Python. I'd never really done much with Python in the past, and this was a nice way to learn how to use Python. So now I'm pretty well versed in how Python works, and I actually really like the language. And something else that I appreciate is how people make user interfaces. I did struggle a little bit even getting the simple user interface that I have up there, because I'd never done it before. So those of you who can make a really good user interface, I applaud you, and don't take that skill for granted, because it's not as easy as it sounds. But yeah, so that is my presentation. Do you guys have any questions?
What would be like the requirements for, I guess, running this on the computer side? So like, could something like a Raspberry Pi use this out in the field, or?
Yeah, a Raspberry Pi can use this out in the field. For the Raspberry Pi, you just need a power source. You just need this little adapter, the antenna, and then you just need basically my software, which is just
in terms of like power of the computer itself, I guess.
Oh,
Super high.
no, it really isn't. You can use these on Pis, even like the base model Pi. You can use this. You don't need much memory. You don't need much processing power. You don't even need much hard drive space for the files and stuff. So it's a very simple software and program to run, and the requirements are very, very low.
Which GUI framework did you use?
I used WX Python to make what I made. Jordan?
Is that the reason why you chose to use Python?
No. I chose to use Python because I originally wanted to use C++ as my language of choice, but then I discovered that through C++, it would have taken a lot longer, and there was a library already out there with essentially pre-developed blocks of code that, while not perfect, is a better starting point for me than trying to create all of those from scratch. So then I switched to Python so I could actually use that library.
So what would you say was your biggest challenge?
Biggest challenge would probably be in the fall. I was having problems with my C++ that I wanted to use, and it wasn't until about a month and a half in that I realized this would be a lot harder to do it in C++ and then switch. It's just easier to switch to the Python and then try to make something in Python. I'd say that would probably have been my biggest challenge, and from there on out, it was just a matter of making sure everything else kind of worked together.
So earlier in the presentation, you said one thing you would change that you wouldn't use a VM anymore. What were your initial reasons to use the VM, and what would you have to change in order to make you not have to use it anymore?
So I ran into some issues setting up the libraries and the environments in Windows. And after doing some reading on the library itself, they had said it was developed in Linux and it's meant for Linux, and it was kind of brought to Windows after the fact. And I decided I've never done a virtual machine. I think that'd be kind of fun. I can get an image of Linux. I can get that up and running in almost no time, supposedly. And sure enough, I was able to get that up and running. But the environment itself still took a little bit longer to get set up. But once I did, it was a lot easier to work with in Linux than it was when I tried to get it to set up in Windows. But then once I got all that set up, I realized a couple months ago some of the actual limitations of the virtual machine with USB devices.
So in order to not use a virtual machine, you would just have to have a computer that naturally runs Linux.
Yes and no. You can still get away with using Windows or Mac OS. It takes a little bit longer to set the environment up into those operating systems versus using Linux.
Yeah.
Marissa?
You said that you ran into some troubles reading through the USB through the virtual machine. How did you overcome those? Because I had the same issues. I was trying to read through the USB on a Replit project, and it wasn't even connecting or saying that there was any type of USB found.
So the first couple issues I have is, as I mentioned, the drivers for this device when I first got it are not meant for my project. So the first thing that I had to do was, even though I got it working on my Windows computer, get those drivers working on the virtual machine. And once I got those drivers working, it still wasn't the easiest to get the digital data, the converted data from the device into my actual program itself. It had errors reading it, and it was just a lot of trial and error more than anything, and a lot of research from what other people had tried. And I found something that worked. But then once I got that working, I still had issues with the device not relinquishing its control. And the VM would say, oh yeah, I don't have control of the device anymore, but then there was nothing with control of the device. And then I just had to unplug it and reset the device essentially. So I don't know entirely what that was all about, but from what I read, that's just an issue that virtual machines have, from my understanding of it.
Okay. Great. Well done.
Thank you.